Welcome to The Explainer. Today we're diving into a super critical question about AI. Just because a model is accurate overall, can we actually trust its individual predictions?
Okay, so let's start with a little thought experiment. Picture an AI working in a super high-stakes field, maybe medicine, and it's got this incredible 99% accuracy rate. I mean, on the surface, that sounds amazing, right? A total A-plus student?
But what about that other 1%? You know, in a life or death situation, when you're talking about a single medical diagnosis or a split-second decision from a self-driving car, can that one single wrong prediction be totally catastrophic?
The answer is absolutely yes. And that's really the core problem here. A model can have a fantastic average score, but still make these huge, really consequential mistakes on specific predictions. And that's the big challenge we're going to unpack today.
All right, let's break this down. This gets us to our first big point, the huge difference between a model's average performance and how reliable it is on any one single specific case.
This whole thing is known as the problem of pointwise reliability. And honestly, it's a massive barrier to using AI in really critical areas. Think medicine or autonomous cars, where, just one mistake is one too many. You just can't trust the average when a life is on the line.
So, how have we traditionally tried to solve this? This brings us to the existing toolkit, the old ways we've tried to measure an AI's uncertainty.
Okay, so there are basically two main approaches. On one hand, you've got integrated methods. These try to build a sense of uncertainty right into the AI from the get-go. They can be really powerful, but they're often super complex to set up. Then you have auditing methods. Think of these like external fact-checkers that you apply to a model after it's been trained to look for weak spots. The big plus here is that they're way more flexible.
But here's the catch. A lot of these auditing tools have a major blind spot. They basically use a simple ruler, something like Euclidean distance, to figure out if a new piece of data is similar to what the model saw during training. It's kind of like measuring the distance between two cities in a straight line on a map, completely ignoring all the actual roads, mountains, and rivers in between.
And that's a huge problem. See, deep learning models don't use a simple ruler. They create their own really rich, complex internal maps of the data. Using a simple distance measure on them is like giving a pilot a road map and expecting them to navigate the skies. It just doesn't capture the right kind of complexity at all.
Okay, so this is where a new idea comes into play. It's a new kind of AI auditor that's designed for the modern age of deep learning. It's called Resampling Uncertainty Estimation, or RU for short, and its core idea is actually brilliantly simple. It just asks this question: what if I had trained this exact same model, but on a slightly different set of examples? If the model's prediction for a specific point changes a lot, well, that suggests it's not very confident, right?
So here's how it works. First, RU just analyzes the final trained model. Then, and this is the clever part, it simulates being trained on lots of slightly different versions of the original data without actually doing the full, slow retraining. From that, it generates a whole bunch of possible predictions for a single input. Finally, it just measures the spread of those predictions. A wide spread means high uncertainty, a tight cluster means high confidence. And the key is that it does this super fast, making it an incredibly efficient auditing tool.
So what's the secret sauce here? What makes RU so effective? Well, it really comes down to how it decides if a prediction is trustworthy or not. RU basically checks two things. First, it asks the density question. Are there enough similar examples to this one in my training data? Basically, have I seen something like this before? Then it asks the local fit question. For those similar examples I did see, did I perform well on them? If the model can say yes to both, then it's a pretty good sign the prediction is reliable.
Now this next part is what's really interesting. It's all about how RUE defines similarity. Remember how we said those older methods use a simple one-size-fits-all ruler? RU just throws that ruler right out the window. Instead, it uses the model's own unique map of the world. It judges new data based on the model's own internal learned understanding. It's basically using the model's own brain to check its own work, which is, that's its key advantage right there. It's a brilliant way to do it.
Okay, so the theory sounds great, but how does this actually stack up in practice? Let's look at the tests.
Well, in experiments across 8 different benchmark datasets, RU was consistently better at spotting incorrect predictions than other after-the-fact auditing methods.
You can see it right here in the chart. That higher score for RU means it's just plain better at telling the difference between a good prediction and a bad one. And what's really amazing is that it's also competitive with those super complex integrated methods, the ones that have to be built in from the very beginning. So with RUE, you get these really high-quality uncertainty estimates without needing all the specialized, complicated training procedures. It's kind of the best of both worlds.
So here's the bottom line. RUE makes reliable uncertainty estimation way more accessible. It gives us a really powerful tool to check a model's work after it's been built. And that makes it so much easier to add that crucial layer of safety and trust to all the AI systems that are already out there.
And that's why this is such a big deal. You see, methods like RUE, they could be the key to finally increasing the adoption of machine learning in those high-stakes fields like medicine. It helps us move beyond just a general sense of, is this model accurate, to a much more important question, can I trust this specific prediction?
And this brings us to a final, forward-looking question. If we can build tools that tell us precisely when to trust an AI's prediction and when to be skeptical, what new, high-stakes challenges can we finally feel confident enough to let AI help us solve? Thanks for joining us on The Explainer.